numbers. These three products also add together. The green group minus the red group, the results will be exactly the same as you do by this calculation. It is just so happen by contingency they are the same. Either way, you would be able to calculate what we call the determinant of 9 numbers arranged in this manner. Now, we learned this before in calculating cross products. The calculation of cross products of two vectors with 3 components arranged in this way, and then replace this by I, this by J, and this by K. It means replace this by I, replace this by J, replace this by K. The calculation result is the cross product of two vectors, one with 3 components put at here, the other is the 3 components put at here. Exactly the same. And in fact, this is the origin. The calculation of the cross product of two vectors follow this definition. Just follow the way of working. Now that is the background. And then with this one, we can calculate something we call the determinant of 9 numbers arranged in 3 by 3 manner. Now here are a couple of examples. By using the definition, this 3 is this one, and then times the determinant of this, which is 7 minus 8, which is 15. And 15 times 3 is 45. I just write it down, 45. And then this 5 times minus 14 minus 88. Minus 14 minus 88 is 74. 74 times 5 is 370. 370, I write it down. And then originally it is minus, so minus 45 minus this one is minus 370, and then 4 times minus 2, 22. So it is 24 minus times 4 is minus 96.喂，早晨。係啊，我呢度係 AC2 250啊。嗰個 visualizer 唔 work。係啊，你而家可以喺個 cam 嗰度望一望啊。係啊係啊，你睇到嘅應該。好啊，唔該你，拜拜。 not work. Now, the visualizer does not work. We use the PC in this way. Now I do it once again. 3 times this 4 2x2 manner is -7 minus 8, which is -15. -15 times 3 is -45. And then the second one, which is 5, these four numbers is -14 plus or minus 88. So it is -74 times 5, which is 370. And then the number 4 with these four numbers, 2x2 is -2, and then -11. It means -13. -13 times 4 is -52. You add up these three numbers, which is -467. Same as this one. Now similarly for this one, we do the same. We do similar calculations. Which is start with these two. Yes. Yeah. 係，我用隻電腦先答你咧。可唔可以今日一定搞掂？因為今晚7點至10點咧，我都會喺度上堂。嗰陣我一定要用呢架，如果唔係上唔到堂。OK， 啊，唔該你。Now we for this morning and this evening I will be coming back again to here and it will be a 3-hour session from 7 to 10. I will be working on the first one. The second one is this minus 6 to minus 9, which is 2 plus 9 is 11. 11 times minus 6 is minus 66, but it is minus 66 becomes add to 66. And then this one, these four numbers, determinant is 2 minus 24. It means 22 minus 2 minus 24 becomes minus 22. Minus 22 times 2 is minus 44. Now you add together, it is 0. This is this 0. Now these two are examples for calculating a 3 times 3 by using this definition. And any 9 numbers arranged in this manner, 3 by 3, can be calculated by using this formula, which is defined. It is a definition. A definition of calculating the determinant value of 9 numbers arranged in this manner, 3 by 3. The way is to use this formula to reduce them into 3 2 by 2, and then the 2 by 2 follows this definition to calculate the value. Now that is how determinant value is calculated. And this extends to 4 by 4 and then 5 by 5 and so on. 4 by 4 can be reduced to 3 by 3, 3 by 3 reduced to 2 by 2, and then use the definition of 2 by 2, this product minus this product. N by n reduced to n minus 1 by n minus 1, and then n minus 1 reduced to n minus 2, and so on until it is reduced to 3 by 3, and then reduced to 2 by 2. And then by 2 by 2, we use the formula this product minus this product. This is how determinant value is calculated, and this is definitions. And this definition has been made some 200 years ago, and it has been used for billions of times in many different situations for calculating numerical values when they are arranged in n by n array manner, which is called determinant. Now, with that background, there are some more that we can do. First, these two are definition of two names. When a square matrix A's determinant is calculated to be 0, then this matrix is called singular. When the determinant value is non-zero, it is called non-singular. It's just a word of describing some characteristic of a square matrix. Now, this, whether it is singular or non-singular, numerical value of the determinant is just 0 or non-zero. However, this numerical value is very important. When it is 0, it means that its multiplicative inverse does not exist. If it is non-zero, then its multiplicative inverse exists and unique. We will come to that later today. Just a characteristic of determinant. It is one of the importance of the calculation of determinant because the numerical value, whether it is 0 or non-zero, determines whether its multiplicative inverse exists or not. And later I will explain to you why the existence of multiplicative inverse exists or not is so important, especially to you who are studying information system development, writing programs. It is so important to you. This one we will talk about later today. Two more definitions. One is called minor, the other is called cofactor. What is the minor of a matrix? Now, in fact, we look at a matrix of equal number of rows and columns. In every position, there are 9 positions at here, 3 by 3. Every position's minor is the determinant of the numbers disregarding the row and column in that position. Now look at one example and here. This numerical example. Now these two are the position, first row, second column. It means this position. Do not care about the value, just the position. Forget about the row and the column of this position. Leaving behind are line numbers. Copy them with their relative positions unchanged. -1, 5, and 3. 3, -1, and 1. 9, 8, -2. 9, 6, -2. 9, 6, -2. Copy them, making them into another square array of numbers. Now it is 3 by 3 array of numbers. And then take the determinant value of this 3 by 3 using the definition of 3 by 3, and then we can calculate it to be 160. Now we can do it once again as I practice. -1 times -2 is 2. 2 minus 6 is -4. And then times -1 is 4. Memorize 4 first. And then these 4 numbers, -10 minus 18, it means -28. -28 times 3 is -84. But this one has to be -8, so -84 is 84. 84 plus the original one, which is -4, becomes 80. No, not 80. It is 2 minus 6, and then minus is 4. So 84 minus -4 is 88. And then this one is 5 minus -3 is 8. 8 times 9 is 72. 72 add to 88 is 160, which is this one. So the minor of this position is the determinant of these three columns, which is calculated to be 160, which we have just done. Okay. Another example, the minor of this position 2, 4, second row, fourth column. Forget about the second row, forget about the fourth column. Leaving behind are line numbers. Copy these line numbers with the relative positions unchanged. 4, 5, 3. 0, minus 5, and 7. And then 10, minus 1, and 1. This 3 times 3, determinant value, using the same calculation. 4 times this 2 by 2, 5, minus 3 becomes 8. 8 times 4 is 32. Memorize 32. And then 0 times whatever is 0. And then this 10, 2 by 2 is 35. Minus 50 is 35. 50. 50 times 10 is 500. Originally it is 4 times 5 minus 5 minus 7 is 5 minus 7 minus 5 minus 7 is minus 2. Anything more? 正七會議程4負8 sorry. Minus 5 minus 7 is minus 5 add to 7, which is positive 2. Positive 2 times 4 is positive 8. 35 minus 15 is 35 plus 15 is 50. 50 times 10 is 500. 500 add to originally 2 times 4 is 8. Therefore, the answer is 508. This is the determinant of these line numbers, and which is defined to be the minor of this position. Second row, fourth column. Okay? Now that is the definition of minor. 冇咗個 visualizer 真係好麻煩。Although it is worked out for you, but I want to work it out directly. We do not have it. Try it again. We have to rely on this. Okay, this is minor. For every position in a matrix, we can determine the minor of every position. Now, I say position. Every position's minor is determined by this way. You do not have to care about the original value of that position. It just ignore, forget the row and column of each position, and calculate the determinant of the rest of numbers, and that is the minor of that position. Every position has a minor. It is always be able to be calculated. This value is always to be calculated. No matter it is positive, negative, or zero, or even complex number, we will always be able to calculate for the minor of a position. It must be a number. It can be positive, can be negative, can be zero, can be real, can be complex. It is always be able to be calculated. For every position, there is a minor. Okay? It is a value. The other definition is cofactor. Cofactor follows minor. Now remember, I repeat once again, every position has a minor, which is the value of the determinant by forgetting the row and column of that position, calculates the determinant value of the rest of numbers. And that is the minor of that position. It is a numerical value, a determinant value of that position. And then cofactor is just the minus with some change in the sign of the numbers. How to make this change? Now it follows a pattern of this arrangement. Alternatives of positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. In this pattern, just alternatives of positive and negative. Impose this positive and negative pattern to the matrix of the minus of a matrix. Say this one will be positive, negative, positive, negative, negative, positive, negative, positive, positive, negative, positive, negative, negative, positive, negative, positive of the minus. Say in this position, first row, second column, we have calculated the minus is 160. So the cofactor of this position is positive, negative. It's negative 160. It is the cofactor of this position in this matrix. Similar for this one, second row, fourth column. So positive, negative, positive, negative, positive. The same as you do it this way, positive, negative, positive, negative, positive. The calculated result of this minor is 508, and it is positive of 508, which is the cofactor of this position. Whenever it is positive, the cofactor is exactly the same as the minor. Whenever it is negative, the cofactor is the negative of the minor value in that position. It is just the difference between cofactor and minor. Now, once again, follow this pattern. Whenever the position is positive, the cofactor is the same as the minor. Whenever it is a negative, then the cofactor is the negative of the minor value. And since minors are numbers, every position has a minor. Putting back into the same numbers of array, the resulting matrix is called the matrix of minors. Similarly for cofactors, putting back into the same arrangement of arrays, the matrix is called the matrix of cofactors. Now, here is an example. You are given this matrix. For each of the positions, we can calculate its minor. Say for this one, M11, the minor is 4 minus 6 is minus 2. And the cofactor is, first position is positive. So in the matrix of minus, this position is minus 2. In the matrix of cofactors, since it's positive position, therefore the minor and the cofactor is the same position. For the second position, this one, the minor is 4 minus 4 is 0. So in this position, the minus is 0. Now, if it is 0, no matter if it's positive or negative, it is also 0 in the matrix of cofactors. 0. For this position, the minor is 3 minus 2, which is 1. And then it is positive, negative, positive. So the cofactor is also 1. This position, the minor is 12 minus 3, which is 9. And positive, negative. So the cofactor is minus 9, which is this one. For this position, the minor is 4 minus 2, which is 2. And it is positive, negative, positive. Therefore, the cofactor is also 2. For this position, the minor is 3 minus 6. It is minus 3. And it is positive, negative, positive, negative. So negative of this one is positive 3 in the matrix of cofactors. For this position, the minor is 6 minus 1 is 5. And it's positive, negative, positive. So cofactor is the same as minor. For this position, the minor is 2 minus 1, which is 1. And positive, negative, positive, negative. So cofactor is minus 1. This last position, the minus 1 minus 3 is minus 2. And the position is positive, negative, positive, negative, positive. So it is the same as the minor. And relative to this matrix, the matrix of minors are these 9 numbers. The matrix of cofactors are these 9 numbers. Okay. This is definition of minors and cofactor of a given matrix. We have seen the calculation of the determinant of a matrix by using this definition. Now, in fact, this calculated result can be determined by the calculation very similar to this one, but you can choose any single row or any single column. Any single row or any single column. Follow this definition to calculate the determinant of a square matrix. It doesn't matter which row or which column. Just use one row or one column. Then we can calculate the determinant of a matrix. Let us take an example. We take a simple one. Say the question 3 in tutorial 9. Which is this one. This one. I use the first column to calculate its determinant, which is 1 times 3 minus 8, which is minus 5, and then 1 times 7 minus 24. 7 minus 24, which is 31, but positive, negative. So minus 31. And then 4 times 7 minus 9, which is 16. 16 times 4 is 46. Positive, negative, positive. So 64. And then minus 5 minus 31 plus 64 is 28. Now, this is by using the first column. How about by using the second column? It is 7 times 2 minus 4, it is minus 2. Minus 2, which is times 7, it is minus 14. But this is a negative position. So, note 2. 1 minus 4. 1 minus 4, I have to write it down. 1 minus 4 is minus 3. Minus 3 times 7 is minus 21. Minus 21, but it is this minus position becomes positive 21. I write it down positive 21. And then for this position, it is 1 minus 12. So it is minus 11. Minus 11 times 3 is minus 33. Positive position. So I write down minus 33. And then for this position, it is 1 minus 3 becomes 4. 4 times 8 is 32. Positive, negative, positive, negative. So it is minus 32.
Tiếp sau. Có tạp cáo xin cho buổi nào không? Dạ tin còn vậy á. 我7點半醒咗㗎啦，之後再瞓翻起身，變咗8點半啫嘛。係喎，我 send 咗條 link 出嚟咯。
我知啊，我拉咗啦。
睇咗。
我係咪最靚？睇你哋嗰條片，同你精神嘅直直。
多謝。
其實你一個follow我
我知。多謝。多謝大家嘅支持，我會繼續努力。
你哋嘅技術做得
Now, we use this one and then we calculate
第一版睇下。單面印刷嚟㗎嘛。
你明白得唔得？啲人就係你睇個題目，
29嘛。
跟住望咗啦，先。
7 times
16版啫，16版。
7 times these four numbers. 1 minus 4. And then positive, negative. So it is negative. Positive, negative, positive. Plus 3. And then 1 minus 12. Positive, negative, positive, negative. X times 1 minus 3. What is better? Yeah.
这跟你放的还是有的。
好啊。
那你就后面就下了。
即係 x 加 y 等於174，2x 3y。噼里啪啦。
然后就没说。
哔哩哔哩。
在台州，对吧？基本上快的。
追住個鏡頭先。唔得直播嚟。
I calculate all the line minus first. First one is do it this way. First minus is 3 minus 8, which is minus 5. And then for this position, the minus is 1 minus 4. It will be minus 3. And for this position, the minus is 8 minus 12. So it is minus 4. For this position, the minus is 7 minus 24. Okay? So it is 17. Oh my god. 31. 24加7 31. For this one, the minor is 1, and then 呢一邊咧就係3、4、12，減咗12 13。
減成13啊！
For For this position,
3、
the
7、
minor is
28。
8 minus 28. So it is minus 20.
22、負20。
For this position, the minor is 7 and then
33、
minus 9.
7減9、7加9。
16. For this position, the minor is 1
減
minus 3. So 4. And then the last position,
負4。
the minor is 3 minus 7. So it's minus 4.
即係正負正負正負。
Okay? And the cofactors inside of some of the numbers, which is 3. And this is minus 31. This is 20. And this is minus 4. These are the cofactors. And then the determinants, you use the cofactor of each of any row or any column times the original number. Therefore, now, by using the first column, minus 5 times plus minus 31, and then plus 4 times 16, which is the original one that I did here. Minus 5 minus 31 plus 64. If we use this column, then it is 21 plus 39, 60. 60 minus 32, 28. For using this one, 12 plus 20. So it is 32. 32 minus 4, 28. For this row, minus 5 plus 21, it is 16. 16 plus 12, 28. For this row, minus 31 plus 39, it is 8. 8 plus 20, 28. For this row, 64 minus 32, 32. 32 minus 4, 28. So we try all these 3 rows and 3 columns. All are 28. Okay? Therefore, you get the matrix or cofactors. Choose any row or any column. Just one row or one column. Multiply to its original numbers correspondingly. Just like a dot product. Okay? You choose any row or any column, the dot product of the original row or column with the cofactor row or column. Then you will get the determinant. Okay? We demonstrated here for the 3 columns and the 3 rows. In each of the 6 times, 6 trials, we get 28 from here. Okay? That is what is like. You can choose any row or any column from the original matrix and the same row or column from the matrix or cofactors, take the dot product. That is the determinant of the matrix. Okay? This is another example. You can read by yourself. I think it's the same as what we did before. This one, we can produce the cofactor matrix, and then you really need to calculate. Here are some examples. Can you do it by yourself by reading this? Okay, as what I did. And here, you make up the cofactor matrix and then choose any row and any column. Do the dot product. Time is running out, so I think I better carry on because the facility is not good today. Transport is something easy. Transport does not demand square matrix. Any matrix can be having its transport. Transport just puts column into rows, or conversely, putting rows into column. Say in this example, it is just one column. Its transport is putting this column into row. So it is originally column is 2x, now the row is 2x. Column in row. In this example, the first column is 1, 4, 7. Put it into the first row. So the first row is 1, 4, 7. Second column is 2, 5, 8. Put it into row. So second row is 2, 5, 8. Similarly, for the third column, put it into third row, 3, 6, 9. Third row is 3, 6, 9. Now, if you do not want to do column to row, you can do row to column. First row is 1, 2, 3. Make it into first column, 1, 2, 3. Second row is 4, 5, 6. Make it into second column, 4, 5, 6. Third row becomes third column, 7, 8, 9. Third column is 7, 8, 9. Okay, that is called transport. For this one, the same. First row is 1, 2. First column is 1, 2, 0. It becomes row 1, 2, 0. 2, 1, 0 becomes second row 1, 0. 0, 0, 1 becomes the third row 0, 0, 1. Okay. Two column transport becomes two row. First row, second row. Okay. This is called transport. Now, this one is a transport of this one, or this one is a transport of this one. And then if you take the transport of this transport, first row becomes first column, second row becomes second column. This one, first column becomes first row, second column becomes second row, third column becomes third row. That's why the transport of the transport is itself. Transport of transport is itself. Transport of this transport is itself. Okay? Whenever the transport is the same as itself, we call this matrix symmetric. Now, if a matrix, if you do not read the diagonal entries, then all the others are mirror image to each other, making the diagonal as the mirror. Then the matrix is symmetric. Okay, you see? Treat this pen as a mirror, then it is -3, -3. Now treat this pen as a mirror. You see, 4 and 4, 5 and 5, 0 and 0. Whenever you see such pattern, its transport is the same as itself. And we call such type of matrix a symmetric matrix. Now that is what I want to say about determinant and transpose. Here is just an example showing you that the transpose of a product of two matrices, you are given two matrices A and B, you multiply them up in this manner, A times B, the result is this one. If you take the transpose, this becomes the first row, this becomes the second row. And then you take the transpose of this first, and the transpose of this, you multiply the transpose of this one to the transpose of this one. You get the result which is exactly the same as this one. Therefore, we have this formula, A times B's product transpose equals to the transpose of B times the transpose of A. Reverse their order. The transpose of a product equals to the product of the transpose, but reverse the order. You can see in here. Now, it does not mean too much to you. And here are some properties of determinant. I'm not going to prove everyone for you. Some are always, this one, this one, this one, and this one, and this one are always. This one is quite difficult to prove. And in examination, there will not be questions on proving of this. Just use them. You do not need effects. In the examination which to come next month, you need only this one. Okay? The others not necessary in the examination. Let me see whether it works now or not. And for next chapter, I still have to use this one. Now, this chapter, I introduce something which is very important, especially for you who study computer programming. Now, I saw this on the internet. Everybody knows that I seldom use electronic calculator, and I saw this in the internet. I copy it to be the cover page of this set of slides. This tells you this model of an electronic calculator can be used for calculating some properties of matrix. And here it is the inverse of a matrix. Now I do not know whether your electronic calculator can do this or not. I do not know whether you can do it or not. However, inverse of a matrix is particularly important in the sense of closing to the end of this topic, which is this one. A system of equations can be written into this manner: coefficient matrix times the column vector of the unknowns equals to the column vector of the constants. Say this one. Not this one. Yes. Here are three equations. We can write the three equations into a matrix equation. If you cannot recognize them, 少拉加嘅。So I use this again. Okay, now you look at this system, and then now you memorize this one, and we go to here.
醫生話食藥，唔係會喺體內殘留㗎，長期食藥會有依賴㗎，就必理痛。都係。
唉，搞掂。哇！仲有唔係好多時間。
但係呢個機就
頭先有喎，頭先嗰個姐姐試咗嘅喎。你隻手先得嘅喎，佢有㗎。Now, okay, we can use this now. This is much better.
但係呢邊睇唔到喎。
Now, which is much better now? We do it in a fast pace. Now, 點解長咗嘅？
但係一樣嘅喎。
唔緊要啦嚇，咁都好過冇。Now，兩邊唔同嘅點解？係咯，兩邊唔同嘅。得翻。Okay, now, what is inverse? When we are talking about inverse, it is multiplicative inverse. Multiplicative inverse, it means the inverse applies to multiplication. Inverse means you are given a matrix. The inverse of it is you multiply them together, it will produce the identity matrix. No matter you multiply from on the left or on the right, it will produce the same identity matrix. Identity matrix means the matrix with all the diagonal elements are 1, the all others are 0. And the identity matrix is when it multiplies to whatever matrix, it does not change that one. Just like you multiply positive 1 to a number, it means you do not do any multiplication. Same as identity matrix. You multiply the identity matrix to whatever matrix, it does not change it. as if you do not have done the multiplication. For any other matrix, if you can find another one which you multiply them together, it produces the identity, then we say these two matrices are inverse to each other. And it can be shown that the inverse of a matrix is unique. It means a given matrix, if it has an inverse, then it must be that one. Now, not every matrix has an inverse. Not every matrix has an inverse. Some do not have inverse. No is no. Okay? 冇就係冇啦。Some have inverse. Some do not have inverse. When if it has, then it must be unique. There's only one. One has this. If it has an inverse, there is only one inverse. And the inverse of a matrix inverse turns back to itself. It means if B is the inverse of A, then the inverse of B is the same as A. A is the inverse of B, then A's inverse is B. Okay? Just like transform. It's not difficult to prove because B equals to A inverse, then B's inverse times B equals to identity, and this one is the same as this one, right? So we can write B's inverse. A inverse is B, and inverse is B's inverse times B. B is A inverse, okay, which is the identity. Now, I write it once again. B equals to A minus A inverse. Now, the inverse of A is written as A minus. Here, you look at A minus. And B's inverse times B equals to identity by definition. We have the same as A times B. Now B equals to identity. A times B also equals to the identity. They are the same. Therefore, B's inverse is A, right? I write it on this side. B inverse A. B. Because both equals to the same identity matrix. A times B is identity. B inverse times B also identity. Definition. Okay, both are definitions. We can see B inverse is the same as A. Now, originally, B is A's inverse. Now we have seen that B's inverse is A. Once again, B is the inverse of A, and B's inverse is A. Okay? Now, read it once again. B is the inverse of A, and B's inverse becomes back to A. Okay? B is originally the A's inverse, and B's inverse back to A. You can check from here. B is originally A's inverse. And we have seen B's inverse, by definition, is the identity matrix. From here, by definition of B being the inverse of A, then we write B times A equals to A inverse times A, which is identity again. Okay, so all these are the same. Therefore, we can see what? And this is the same as A times B. Okay, from here. By definition, A times B equals to B times A equals to the identity. Therefore, take this away. This one equals to this one. B is the inverse of A. B's inverse back to A. Okay? Now, this is inverse. And then, this is a numerical example. A matrix times its inverse is the identity. Reversed order, and then we check it is also the identity. Therefore, we will have verified that A times B equals to B times A if A and B are inverse to each other. Now, there are two ways of finding the inverse of a matrix if it exists. One of the ways is, say, for this matrix. Now, we do not know whether it exists or not, but if it is 3 times 3, we do like this. Append the identity matrix on the right of it, like this. Originally, it is this matrix. Then, put the 3 times 3 identity on its right. Becomes 3 rows, 6 columns. And start from this matrix, perform the elementary row operations, which I have done all steps for you with explanations on the slide. Say, multiply the first row by -2 and then add to the second row. And then multiply the first row by -1 and then add to the third row. We get this one. And then multiply the first row by 2, the second row by 2, and then add to the third row. We get this one. And then multiply the third row by -1. We get this one. And then multiply the third row by -3, by 3, and then add to the second row. We get this one. And then multiply the second row by -2, and then add to the first row. We get this one. This is the process. I have written down all this for you. Whenever you get the left-hand side becomes the identity matrix, the right-hand side is its inverse. Now the proof of it is not difficult. The proof is at here. This is the proof I've done. And you are not asked to prove this in the course, and you will not be asked to prove this in the examination. I just verify that it is true by proving it. It is by matrix algebra. We can prove it. Therefore, this is the way of getting the inverse of a matrix. Now, if whenever you find any situation, the left-hand side of any row are all 0, it means that the inverse does not exist. No matter what's on the right-hand side, so long as you get the left-hand side are all 0 in any of the row, then it means the inverse does not exist. Now, once again, nobody said that inverse must exist for a given matrix. Some matrices do not have inverse. By using this method, if you see at any instant you find the left-hand side are all 0, you do not need to care about the right-hand side. once you get any row which is all 0 on the left hand side, you may say inverse does not exist. But if you can work up to this form, left hand side is an identity matrix, then the right hand side is the inverse of the original one. The original is this one. Okay? So after the elementary row operations, when you arrive at here, then this is the inverse of the original matrix. Okay? Then we can write the original matrix is A, which is this one. Start with this matrix and elementary row operations until this form. The right hand side is this matrix inverse. This is one of the ways to find inverse. The second way is, remember we have the cofactor matrix, the matrix of cofactor of for whatever given matrix, you will always be able to find the matrix of cofactors because every position has a minor, and then by using the pattern positive, negative, you change the sign appropriately, you find the matrix of cofactors. With that cofactor matrix, take the transpose of that cofactor matrix. Transpose means put all the columns into row or put all the rows in the column, either way. The result is called adjoint of that matrix. The transpose of the cofactors is called the adjoint of A, written by this form. And you can calculate the determinant of any matrix. If it is non-zero, then we take the reciprocal. The reciprocal determinant times the adjoint, it means the transpose of the cofactor. It is the inverse. It can be proved. Very difficult, this proof, but it is true. And if it is non-zero, we call this non-singular. Remember in the very early of this lecture, if it is 0, it is singular. What I said that the usefulness of singular or non-singular is here. If it is 0, we cannot write it this way. It means no inverse exists. If it is non-zero, we can write it this way, inverse exists. Because adjoint is always existing. It is just the transpose of the cofactor matrix. Cofactor matrix always exists for whatever given square matrix. Okay? So it is called determinant. It determines whether the inverse exists or not. If it is 0, no inverse. If it is non-zero, it is how to find the inverse. Now, to you, it is particularly important because remember this. First, given a square matrix, you can always find the minus. The matrix of minor is nothing you have to think. Just use the way mechanically. Just what I did several times in front of you today. You can always find the matrix of minus. And then apply the pattern positive, negative, positive, negative. Again, nothing to think. Just do it directly. And then with that, hit the transpose. Again, nothing to think. Becomes the adjoint. And then calculate the determinant. Take any row or any column of the cofactor matrix, dot to the original row or column that you have chosen. You can calculate the determinant. Just see whether it is 0 or not. If it is non-zero, apply this formula, which is a scalar multiple to the adjoint. So throughout this whole process, you have not to think anything. Just do it mechanically. It means you can write a program to find the inverse of any given square matrix. First, calculate its determinant whether it is 0 or not. If it is non-zero, take the scalar multiple of it to find the inverse. That is programmable for any given square matrix. It's better than the elementary row operations because in the elementary row operations, you have to decide what next step you are going to do. For this one, no need to think anything. It is just mechanical work. That's why in the internet, you can download free of charge this type of program. And so, in the very early cover page, even the electronic calculator can do. Now you know why electronic calculator can calculate this. Because it's nothing you have to think, just mechanical work. Programmable, this one. Okay? If you study calculus, also, I've shown you how to calculate sine, cosine, tangent, log, exponential by using infinite series. You do not have to think anything. You do not have to draw right-angle triangle to find sine, cosine. Just use arithmetic. We can calculate all those electronic calculators function. It comes to matrix, the same. What's the importance of this one is this. Okay? For every system of equations, just like this one, on the slide, this is these three equations. If you cannot recognize them, I just make it at here. And then from this system, we can see the coefficient matrix is 1, 2, 1, 2, 5, 0, 3, 3, 8. Right hand side is minus 1, 1, 2, which is the same as this one. Okay? We can write in this way, and by using this way, if we can find the inverse of this coefficient matrix, we multiply both sides by the same inverse. The left hand side, this is the inverse, which is the same as what we saw before, the same one. This one. Okay? And we have found that the inverse is this one. And if we multiply both sides by this inverse, left hand side becomes identity. Identity times this one is this one. Right hand side, we multiply the inverse to the constant, we get this. And so, this is the solution. X equals to 38, y equals to minus 12, z equals to minus 5. This is by using the inverse. I also have shown you by using elementary row operations. Just Gauss-Jordan elimination. This is, I have done it to you, and you get the same result. So, the importance of inverse is that you can make use of the inverse to find solution of x, y, z. Now, once again, in the previous example, remember 15 minutes ago, starting from this matrix, and then with this method, go through these row operations, and then finally we find this inverse, and this is the inverse of this matrix, and then we multiply the inverse to both sides. Left hand side becomes inverse times itself, it means identity. So identity means you do not have to multiply anything. Leaving behind is just x, y, z. Right hand side, we multiply this inverse to this column and do multiplication which is again another mechanical work. You do not have to think anything, just dot product. You can calculate. The result is this vector. And so x equals to this one, y equals to this one, z equals to this one. Now, if you want to verify this, you can substitute x equal to 30x, y equal to 12, z equal to minus 5 into these equations. You find right hand side equal to minus 1, 1, and minus 2 verification. Another way to do is by doing something what we learned last time, Gauss-Jordan elimination on the augmented matrix. This one, I do not need inverse, but only Gauss-Jordan elimination. I've worked out this for you. And finally, in this reduced row echelon form, it is 38, 12, minus 12, and 5. Exactly the same as this one. So you can see both get the same result. They are the same. This is by Gauss-Jordan elimination until you get the reduced row echelon form. This one, you use inverse. By using this method, it is just mechanical work. You do not have to think anything. Follow the rule is determine the coefficient matrix the same as this one. No change, no difference between these two methods. By reading the equations, make it up. Like this system, and then from here form the coefficient matrix and the column matrix. And then put it into this form, coefficient matrix, variable column, and then constant. Find the inverse by first make the minor matrix and then cofactor matrix, and then take the transpose become adjoint. Divide this by the determinant of it, then you find the inverse. So these 4 steps are nothing to think, just minor, cofactor, adjoint, and divided by its determinant. You will get this one, and multiply this to the right hand side. Again, nothing to think, just multiplication. You find this one. This is one of the 2 methods. The other is you use elementary row operations, perform the Gauss-Jordan elimination until you find the reduced row echelon form. Then you read the result. Either way, you can get the solution of a system of equations. You will get the same result. This one, you have to think what the next step you should do in order to get this one. For using the inverse method, you do not have to think anything. First thing to do is the minor and then the cofactor and calculate the determinant. In fact, to calculate the determinant, you only need one row or one column in the cofactor matrix. You do not need to do all entries, just any row or any column to calculate the determinant first. If it is non-zero, then proceed. If it is 0, just write inverse not exist. Okay? Then if inverse not exist, you cannot use this way. You have to go back into elementary row operations. Either it's no solution or infinite many solutions. Okay, you have to use this way if inverse does not exist. If the determinant is non-zero, you may proceed by using this way, or use your electronic calculator, because the electronic calculator makes use of this method. It does not make use of elementary row operations. Because any matrix, if it is non-singular, it must work. You do not have to think anything, just programmable. And it is done. and you can download from the internet free of charge. Not easy, not difficult to write this program. Okay? I'm sorry that the machine did not work until these very good classmates who fixed the machine for us, and we have to go through this in a fast manner. I hope that it helps you, and this is important. That's why in assignment 3, I've set up a number of questions in the first part of the assignment 3 for you to practice this one as well as the Gauss-Jordan elimination. It has questions in the examination of this type. Okay? Thank you very much. I have to go now. Thank you. And I have a class in this evening in the same place in this room for working out the assignment 3 together with the class. If you are not so busy, you may also join us in this evening from 7 to 10, 3 hours work. And here, the same venue. Thank you again for this course. 唔好意思啊，我收到好多 email， 唔係問我嘢，老細 send 俾我㗎，老細 send 俾我。係啦，話我辦事不力，話你哋好少填 QQ， 麻煩你幫幫手 ，OK？ 幫幫手，唔該。好。可以，但係佢唔係咁做，所以又係將佢揾入佢屋企，或者入入俾佢化成3:3，每一格都係3:3，係啦，但係每一格都係3:3，每一格都係3:3，所以好多嘅。得㗎，淨係3:3。我平時你係3:3。